Welcome to the May 2025 A-Level Further Maths Core Pure 1 paper. Alright, question number 1, quite a nice intro question, just finding a value of A which gives a singular matrix. For a matrix to be singular, it needs to have a determinant of 0. There's a few ways of calculating the determinant of a 3 by 3. You can see me splitting it up into 3 sections with multiples of the 2 by 2 matrices that are there. And equating that to 0. So we've got 3 lots of 3a minus a, subtract 6 lots of a squared minus 2. The last bit disappears, and we get a nice 3-term quadratic to solve to find the value of a. (6a) subtract 6a squared plus 12 is equal to 0. Divide everything by -6. We get a squared, subtract a. Subtract 2 equals 0. Factorizes quite nicely. So our two values of a which create a singular matrix are 2 or -1. For part B, it tells us the determinant is -108 and that a is less than 0. So using the same approach, I equate my expression for the determinant to -108. Bring the 108 over, divide by -6 again. We get a squared subtract a subtract 20 equals 0. And factorizes quite nicely as well. A plus 4 times a minus 5 equals 0. I'll ignore a equals 5 because it tells me in the question that a is less than 0, so our value of a is -4. Then to find the inverse, there's a few ways of doing it. You can follow various algorithms. I'm going to show you how to do it on a Casio FX CG50. I'm going to multiply it by -108 just to make the numbers nice. When I write the inverse, I'll write it as 1 over -108 at the front. Input the matrix with a is -4, and the GDC will do the transpositions and parts of it to give us the inverse matrix. So 1 over -108, 1 over the determinant, lots of, and then the matrix that came up on the screen a second ago: -8, 24, 6, -14, -12, -3, 10, 24, 33. You can bring the determinant into the matrix and write them all as fractions if you wish. That's absolutely fine. I think it looks a little bit prettier like that. And there we go, question number 1. Question number 2, the hyperbolic trig functions. So first thing I'm going to do is expand out hyperbolic sine of 2x. So it's going to be 2 hyperbolic sine of x, hyperbolic cos of x, equals to 3 hyperbolic sine of x. Bring the 3 hyperbolic sine of x onto the left-hand side to make it equal to 0, and we can factorize out the sine x, if that's the way you like to say it. Sine x times by 2 cos x, subtract 3 is equal to 0. So we split that up into 2 separate parts. The part where sine x is equal to 0, and then the other part will be where cos x equals 3 over 2. Now you may just know that if sine x is equal to 0, then x is equal to 0. But in case you weren't sure, replacing sine x with its exponential form e to the x, subtract e to the minus x all over 2 equals 0. Multiply by 2. Bring the e to the minus x over, times both sides by e to the x. Take natural logs of both sides. 2x equals ln of 1. Ln of 1 is of course 0. 2x equals 0. X equals 0. You could skip that and just jump from sine x equals 0 to x equals 0 if you wish. For cosh x equals 3 over 2. I'm going to replace cosh x with e to the x plus e to the minus x over 2. Times both sides by 2. And then multiply everything by e to the x to turn it into a quadratic, or disguised quadratic. Bring the 3e to the x over, we get e to the 2x minus 3e to the x plus 1 equals 0. You can use a substitution here if you want to. I'm not going to bother. So e to the x will be equal to 3 plus or minus the square root of negative 3 squared. Subtract 4 times 1 over 2 lots of 1. That's the quadratic equations formula there. So e to the x is going to be 3 plus or minus root 5 over 2. Taking natural logs of both sides, we get our two other solutions. X equals ln of 3 plus or minus root 5 over 2. That alongside the x equals 0 gives us the 3 solutions to this equation. Question number 3, the complex numbers question. So we're given that z divided by its complex conjugate is purely imaginary. So a plus bi divided by a minus bi is imaginary. So I'm going to multiply top and bottom by a plus bi. Expanding the top, we'll get a squared plus 2abi, subtract b squared. That's all over a squared plus b squared. Then I'm going to split this up into its real and imaginary parts. So the bit with I is going to go to the right, the bits without I is going to go on the left. So the bits without I, a squared minus b squared over a squared plus b squared. And then we're going to get plus 2ab over a squared plus b squared, lots of I. So now that's in its real plus imaginary parts. We're told that it's purely imaginary, so its real part is going to be 0. So a squared minus b squared over a squared plus b squared is equal to 0. Multiply both sides by a squared plus b squared. We get a squared minus b squared equals 0. Therefore, a squared must be equal to b squared, which is what the question wanted us to show. For part B, we're given that the complex number multiplied by its complex conjugate is equal to 50. So a plus bi times a minus bi is equal to 50. Expand that out, we get a squared plus b squared equals 50. So a squared is equal to 50, subtract b squared. Now taking that alongside a squared being equal to b squared from part A, we can deduce that 50 minus b squared will be equal to b squared. Add b squared to both sides, divide both sides by 2, and therefore we can conclude that b must be equal to plus or minus 5. Then going back to either formula, or just thinking about it, you can work out that a must be plus or minus 5 as well. So our 4 complex numbers we could have for z will be 5 plus 5i, 5 minus 5i, minus 5 plus 5i, and minus 5 minus 5i. Question 4. This is the non-homogeneous second order differential equation. We know it's non-homogeneous because it's not equal to 0. Okay, I'm going to find the particular integral first. Putting y is equal to lambda e to the 3x. Differentiating it twice. And plugging that in, we'll get 9 lambda e to the 3x minus 12 lambda e to the 3x plus 4 lambda e to the 3x is equal to the 2e to the 3x. Grouping those together, we get lambda e to the 3x equals 2e to the 3x, therefore lambda is equal to 2. So a particular integral is 2e to the 3x. That bit will go at the end. Then for the complementary function, we know that if we substituted y equals e to the mx in, we would get m squared minus 4m plus 4 equals 0. That will factorize to m minus 2 squared. Essentially, the discriminant is 0. It's a repeated root. B squared equals 4ac. So our repeated roots is equal to 2. That tells us that our complementary function is going to be of the form a plus bx times by e to the 2x. You could write that as a e to the 2x plus bx e to the 2x if you like. Add the particular integral at the end, and there we have the general solution to the differential equation. For part B, it gives us some initial values. Diving straight in with x equals 0, the b disappears, and we're left with 5 equals a plus 2, so a is equal to 3. Then I'll take the equation we've constructed and just quickly expand that out so we can differentiate it. I didn't need to expand it out. You could differentiate it using product rule if you prefer. Anyway, dy by dx is going to be e to the 6 e to the 2x plus, and then we have b e to the 2x plus 2 lots of b x e to the 2x plus the differentiated 2e to 3x, that's 6e to the 3x. Tells us that dy by dx is equal to 12, so let's set dy by dx to 12, plug in x equals 0, and we can deduce that b must be equal to 0. So our particular solution for this setup is going to be y equals 3e to the 2x plus 2e to the 3x. On to question 5. The method of differences question. So first thing I'm going to do is split up the fraction into partial fractions. So factorize the denominator, difference of 2 squares. We're going to get a over r plus 1 plus b over r minus 1. Multiply both sides by r plus 1, r minus 1. We'll get 4 is equivalent to a times r minus 1 plus b times r plus 1. If we let r equal 1, the a term will disappear, and we'll get 4 equals 2b, b is equal to 2, and when we let r equals minus 1, this time the b disappears, and we get 4 equals minus 2a, so a is minus 2. So 4 over r plus 1, r minus 1 is the same as minus 2 over r plus 1 plus 2 over r minus 1. That means we can essentially rewrite the original summation. We're running from r equals 2 to m of 4 over r squared minus 1. That's going to be the same as summing from 2 to n minus 2 over r plus 1 plus 2 over r minus 1. Okay, so let's start with r equals 2. We're going to get minus 2/3 plus 2 over 1. For r equals 3, we're going to get minus 2 over 4 plus 2 over 2. For r equals 4, we're going to get minus 2 over 5 plus 2 over 3. At this point, you can see that we've got the minus 2 over 3 and the plus 2 over 3, and that's where the cancelling is going to begin. Okay, and then at the other end, we're going to have r equals n minus 1, so the penultimate term, we're going to get minus 2 over n plus 2 over n minus 2. And then the last term is going to be minus 2 over n plus 1 plus 2 over n minus 1. And then we can cancel all the parts that cancel in the way that the method of differences does. So the minus 2/3, the plus 2/3, minus 2 over 4 is going to cancel with the one below that, all the way down, and those two are going to cancel as well, leaving us with 4 parts that remain uncancelled. The 2 over 1, the 2 over 2, the minus 2 over n, and the minus 2 over n plus 1. So the full summation of this particular setup is going to be equal to those 4 parts added together, the 2 plus the 1 minus 2 over n minus 2 over n plus 1. The 2 plus 1 makes 3, and we're going to give everything a common denominator of n times n plus 1, so we get 3 lots of n times n plus 1 minus 2 lots of n plus 1 minus 2n. That's going to be all over n times n plus 1. Expand out the numerator, we get 3n squared subtract n subtract 2. All over n times n plus 1. And that factorizes to 3n plus 2 times by n minus 1 over n times n plus 1, which is in the form the question wanted, where p is 3 and q is 2. And we're done. Question number 6, a bit of geometry with complex numbers on the complex plane. Little diagram here to help us. We've got one root of the cubic 2 plus 4i. These are going to come as conjugate pairs. So the other root is going to be 2 minus 4i, and then we're going to get a real root somewhere. All cubic functions will have at least one real root. The difference between 2 plus 4i and 2 minus 4i is going to be 8. And so if we're forming a triangle with the third root that sits on the real number line, then there's two possibilities. It's either going to be to the left or to the right. We're told that the area of the triangle formed is 12. So doing a little bit of basic, half times base times height, a half times 8 times the height is 12. We know that the height must be 3. So it's going to be 3 more than 2 on the real number line, or 3 less than 2. So our 3 roots are going to be 2 plus 4i, that one we're given, 2 minus 4i, and then the two possibilities for the third root are going to be minus 1 or 5. That's 3 less than 2 or 3 more than 2. So writing our function f of x in a fully factorized form, we're going to get z minus z1 times z minus z2 times z minus z3. I'm going to start expanding it before substituting the values in. I think it's a bit clearer when you do it that way. Expanding out the first 2 brackets, we're going to get z squared minus the sum of the roots plus the product of the roots. And then that would be times by the z minus z3. So there are 2 possible z3s. Quick calculation on the side. Let's do the product of z1 and z2. That's 2 plus 4i times by 2 minus 4i. Comes out as 4 plus 16, which is 20. And the sum of the roots, 2 plus 4i plus 2 minus 4i. The complex parts cancel and give us 4. Okay, so we can substitute those into our function f of x now. So it will be z squared subtract 4 lots of z plus 20 times by z subtract our third root. Okay, so now we'll deal with the 2 possible values of z3 separately. Let's deal with the negative 1 root first. Our cubic will be z squared subtract 4z plus 20 times by z plus 1. Expand that out, you get z cubed minus 3z squared plus 16z plus 20. And the other possibility is when z3 is 5. We get z squared minus 4z plus 20 times by z minus 5. When we expand that one out, we get z cubed minus 9z squared plus 40z minus 100. I do recommend doing your z's with an extra line through it because it clearly distinguishes them from the number 2. All right, question number 7. So this is big partial fractions followed by an integration. For this particular setup, just looking at the fraction, we've got, it's going to be a cubic divided by a cubic, so we've got to treat this as a top-heavy fraction. That means that when we write that as partial fractions, we're going to get a constant at the front, and then b over the x plus 2. We can't split up the x squared plus 3, so I'm going to write that bit as cx plus d over x squared plus 3. All right, multiplying through by x plus 2, x squared plus 3. The first choice for x I've gone with is x is equal to -2. That wipes out the a and the c and the d. So choosing -2 into the left part, we get 28. -2 squared plus 3 is 7. Divide both sides by 7, we can deduce that b must be 4. Then there's no way of eliminating 3 in another way, so I've just plugged in the simplest numbers to plug in. I chose 0 first of all. Plugging 0 into things is quite nice. We get 22 equals 6a plus 12 plus 2d. Subtract 12 from both sides and then halve everything. We get 5 equals 3a plus d. I'll leave that there. The next easy number to plug in without doing too much thinking is x equals 1. When we do that, we get 43 equals 12a plus 16 plus 3c plus 3d. Subtract 16 from both sides. And then divide everything by 3. And then lastly, I'm going to substitute in x equals -1. We get 21 equals 4a plus 16, subtract c plus d. And then it's up to you how you want to go about solving this. We've got a 3 by 3 system of simultaneous equations. I've just tidied that one up a little bit and added it to the 9 equals 4a plus c plus d equation. That eliminates c. So we get 14 equals 8a plus 2d, or 7a equals 4a plus d if you prefer. And going back to the equation from when we let x equals 0, 5 equals 3a plus d, we can subtract the second from the first and conclude that a equals 2. Substitute that back in, you get d equals -1, and then substitute that back into one of the other ones, you get c equals 2. And so our partial fractions are going to be 2 plus 4 over x plus 2 plus 2x minus 1 over x squared plus 3. Part B, the integral, obviously we're integrating the same thing, so we can use our partial fractions to split the big fraction up. I'm also going to split up the 2x minus 1 over x squared plus 3 into 2 separate fractions. That's going to help us integrate it because we can now integrate everything one at a time. 2 is going to integrate to 2x. 4 over x plus 2 is going to integrate to 4 lots of the natural log of x plus 2. For the third fraction, the top's the differential of the bottom again, so we can integrate that ln of x squared plus 3, and the 1 over x squared plus 3 is a standard integral. It's the inverse tan one, where it's x squared plus a squared on the denominator, so a in this case is root 3, so we get 1 over root 3 lots of inverse tan of x over root 3, and we're integrating that between 0 and 1. Plug in 1 in, we get 2 plus 4 ln 3 plus ln of 4, subtract 1 over root 3 lots of inverse tan of 1 over root 3. And then when we plug 0 in, we get 0 plus 4 ln 2 plus ln 3, and of course tan of 0 is 0, so that last bit will disappear. Okay, let's tidy everything up. So we've got the 2 at the front, 4 ln 3 plus, sorry, take away ln 3 is going to be 3 ln 3. And subtract 2 ln 2, inverse tan of 1 over root 3 is pi over 6. So we get 1 over root 3 lots of pi over 6. Then I'm going to raise each constant in front of the natural log up as a power. So 3 ln 3 becomes ln 27, 2 ln 2 becomes ln 4, and 1 over root 3 times pi over 6, I'm going to write as pi over 6 root 3, and then using my log rule, ln 27 minus ln 4 is ln of 27 over 4, we get the answer that the question wanted us to. Question number 8, to give me a bit of space at the bottom, I'm going to do that horrendous thing of writing an answer over the question. I do apologise, it's appalling. I'll write myself a strongly worded letter. So plugging into the numbers into the equation, we'll get sine 1 times by 273.2, subtract 213 lots of cos 1, divide both sides by sine 2t sine t, and substitute in again. That will give us our value of a. Plug that into your calculator, and to 3 sig figs, that's 150. For part B, so first I'm going to plug in the value that we just calculated for a, and then I'll put it into standard linear form and use an integrating factor. So dividing everything by sine of t, we get dx by dt, subtract x, and then cos of t over sine of t, or cot of t if you prefer, is going to be equal to 150. The sine t's cancel, so we're just left with sine of 2t. Then the integrating factor, so we know e to the power of the integral of cos t over sine t, that's going to be e to the natural log of sine t, with the minus out the front. So that's ln of 1 over sine t, or if you prefer, ln of cosec t. Cancel the ln's with the e's, and so we get cosec t. So multiplying everything in our equation by cosec t, we get cosec t of dx by dt. subtract then x cot t cosec t is going to be equal to 150 lots of sine 2t times cosec t. Just tidying that up a little bit now. So cosec t times dx by dt, subtract x cot t cosec t is going to equal to sine 2t to sine t cos t, so it's going to be 300 sine t cos t cosec t. The sine t and the cosec t will cancel, so we get 300 cos of t. Then, recognizing that left-hand side is the outcome of the product rule of differentiating x cosec t with respect to t, we can integrate both sides. 300 cos t goes to 300 sine t plus c. It tells us in the question that when x is 213, t is 1. So we can substitute that in to calculate our constant of integration. Subtract 300 sine 1 from both sides. C is 0.687. Then multiplying both sides by sine of t will leave us with x on the left hand side. We equal 300 sine squared of t. Sine times cosec will cancel, plus the 0.687 sine of t. And that is our particular solution. Okay, for part C, we can substitute x for 0. So 0 equals 300 sine squared t plus 0.687 sine t. Factorize out the sine t. And that tells us actually that the values of t will be 0 or pi within the range. And so I'm going to take, obviously, zeros at the start. So I'm going to take t to be pi, 3.141, etc. So that's 3 hours, 0.14 of an hour is 8 minutes. It's 8.49 minutes or something. So the time on top of 10 o'clock will be 10 plus 3 hours and 8 minutes. For part D, we can set our x to be 300.68. And then solve it. I'm going to use a calculator. So using Casio's equation solver setting, you can just type the equation in as it is and do all the heavy lifting for us. So 300 sine of x squared plus 0.687 sine of x is equal to 300.68. When I solve that, we get 1.57 to 3 decimal places. So that's my value of t. Now, that is pretty much exactly half the time that it took him to get up and down, which suggests that this model isn't particularly accurate. If you're climbing and walking up a hill, you wouldn't necessarily expect to take the same amount of time to get to the top as you would do back down again. You probably get back down faster. So my limitation is that equal time for going up the hill as down is likely to be different. Okay, so we have two curves, 3/4 sin x and y equals tan x plus a fifth. So using the exponential versions of those and equating them, we get 3/4 and then the hyperbolic sign e to the x minus e to the minus x over 2. That's going to be equal to hyperbolic tan e to the x minus e to the minus x all over e to the x plus e to the minus x plus 1/5. To tidy this up, the first thing I'm going to do is try and get rid of the fractions. So I've multiplied everything by 40, and that should do enough cancelling. So we've got the 3/4 and the half on the left-hand side becomes 15. Then we've got 40 lots of the hyperbolic tan, and then 1/5 becomes 8. Next step, multiply by e to the x plus e to the minus x to eradicate fractions completely. So we've got 15 lots of e to the x minus e to the minus x times by e to the x plus e to the minus x. That's going to be equal to 40 lots of e to the x minus e to the minus x plus 8 lots of e to the x plus e to the minus x. Start expanding things out now. On the left-hand side, it's a difference of 2 squares almost. We end up with e to the 2x minus e to the minus 2x, and then expanding the right-hand side and collecting them together. 40 e to the x plus 8 e to the x is 48 e to the x, and minus 40 e to the minus x plus 8 e to the minus x is going to be minus 32 e to the minus x. Expanding out the left-hand side, 15 e to the 2x minus 15 e to the minus 2x. I'll leave the right-hand side alone. Then I'm going to multiply everything by e to the 2x. So it becomes 15 e to the 4x minus 15. It's going to be equal to 48 e to the 3x. Subtract 32 e to the x. And lastly, bring everything onto the left-hand side. And we get the equation we wanted. For part B, I've decided to factorize e to the x minus 3 out of the disguised quartic. So we get e to the x minus 3 lots of 15 e to the 3x, subtract 3 e to the 2x, subtract 9 e to the x plus 5, and that's equal to 0. Therefore, e to the x equals 3 is a solution. For part C, well, if e to the x equals 3 is a solution, then x will be equal to natural log of 3, x equals ln 3. And we can plug ln 3 into our expression for hyperbolic tan of x plus 1/5. So we get e to the x is 3, e to the minus x therefore is a third. 3 minus a third over 3 plus a third plus a fifth is 1. So our point P is a point natural log of 3, 1. For part 2, we're asked to integrate. So we're integrating between -4 and 0, e to the 1 over x squared. I'm going to use a substitution here, u equals 1 over x. differentiate that, we get minus 1 over x squared. And therefore dx is equal to minus x squared du, if you forgive me for splitting the variables like that. If you've not done it that way, that's absolutely fine. You've done it the proper way, but I know that you guys quite like coming up with a substitution for dx in terms of du. So there you go. Carrying out the substitution, we get e to the u over x squared times by negative x squared. The x squareds will cancel, so we're integrating minus e to the u du, which integrates to minus e to the u. Reversing the substitution, I'm going to reverse it in a way that sets a parameter t instead of 0, because if we plug 0 in, we'd be doing 1 divided by 0 in the calculation. So I'm going to put t in as a parameter, and I'm going to let t tend to 0. So plugging t in, the limit of t tending to 0 of minus e to the 1 over t. We're coming in here from the negative side, so t is tending to 0 when it's negative. So we're going to get e to the power of a very large negative number, which is going to tend to 0. As that happens. So the limit as t tends to 0 from the negative side of minus e to the 1 over t will be 0. Plugging negative 4 in is straightforward, just minus e to the minus a quarter. So we get 0 subtract negative e to the negative a quarter, which is e to the negative a quarter, which is what the question wanted. Question number 10. I've decided not to write all over the questions. That would be horrendous. So here it is on neat lined paper. We want an expression for 8 sine to the power of 4 theta. So I'm going to take the equation they've given me for involving sine theta, and I'm going to raise that to the power of 4. So 2i sine of theta to the power of 4 will be z minus 1 over z to the power of 4. 2 to the power of 4 is 16, I to the power of 4 is 1, and sine theta to the power of 4 is sine to the power of 4 theta. Then the right hand side, a little binomial expansion. If you know your Pascal's triangle, 1, 4, 6, 4, 1, you can use that. We're going to start with z to the 4, and then we're going to get z cubed times by 1 over z, which will be z squared. For the third part, you get z squared times 1 over z squared, which will cancel, leaving us with the 6, and so on. If you take more lines to do that, that's absolutely fine. So our 16 sine to the 4 theta, I'm going to rearrange the right-hand side to pair them up. I'm going to pair up the z to the 4 with the 1 over z to the 4. And I'm going to pair up the z squared with 1 over z squared, factorising out minus 4 from that. And then leave the 6 alone. The reason I've paired them up like that is we have it given that z to the n over 1, z to the n plus 1 over z to the n is equal to 2 cos n theta. So z to the 4 plus 1 over z to the 4 is the same as 2 cos to the 4 theta. Z squared plus 1 over z squared is 2 cos 2 theta. And then if we divide everything by 2, we get the equation that was in the question. Okay, for part B, we're calculating the volume of this shape. So volume of revolution, rotating about the y-axis. So we're going to use pi times the integral of x squared dy. Okay, we know that x is equal to sine squared of a half y. So we are going to be integrating between 0 and 8 pi over 5. So sine squared of a half y, square that, we get sine to the power 4 of a half y. And then we can use our answer from part A. Now, if we need an extra 8 in there, so what I'm going to do is take an 8th out, and therefore you can put an 8 inside it and just carry out the substitution. Obviously, theta is now a half y, so 4 theta will become 2y, 2 theta will become y, and we're integrating cos of 2y minus 4 cos of y plus 3, which is straightforward. It's going to be half sine of 2y, subtract 4 sine y, plus 3y, between 0 and 8 pi over 5. And let's plug those in. So half sine 16 pi over 5 minus 4 sine 8 pi over 5 plus 3 lots of 8 pi over 5. Substituting 0 in, straightforward. Sine of 0 is 0. 3 lots of 0 is 0. So no thought required there. And plug that in your calculator. If you do that correctly, you get 7.3 out, rounded to 2 sig figs. That's the volume of our shape. Now it gives us a little bonus question at the end with the density and the mass. So if we take our volume, 7.3, and times it by the density, 0.85, it tells us that our model suggests that it would be 6.2 grams, which I think is pretty close to 6 grams. And therefore, this is a reasonable model. A nice little question to finish off there. And that's the end of the paper. Well done if you managed to get through that last one. All right, bye.